Hello chemistry students, in this video I'm going to go over titrations. Alright, so titration is a method of determining the concentration of an unknown solution using a solution of known concentration. That's going to be referred to as the standard solution or the titrant. The endpoint is when you have added just enough standard solution to neutralize the unknown solution. And if the unknown solution is an acid, the standard solution used to titrate it will be a base and vice versa. Alright, so let's take a look at the anatomy of a titration. So you'll have a device known as a burette that has a valve that can be opened and closed to let the known solution flow into the unknown solution. The unknown solution is referred to as the titrand or the analyte, while the known solution is referred to as the titrant. And you usually put some kind of color change indicator down here so you know when you have reached the end point. So, maybe it's blue to start with and then it turns yellow or something like that. Alright, so let's take a look at some steps for titration. So you're going to have a measured amount of an acid or base of unknown concentration added to the Erlenmeyer flask. And so you measure the amount, you know the volume of it, you just don't know the concentration. Alright, and you'll use an appropriate indicator, which your teacher would probably help you select, or you would have to consult some reference materials if you were doing this, say, as a chemist in a lab. And then you would add to it a measured amount of an acid or a base of known concentration until you reach the end point. So here's the setup again. And you could go through all of these steps to actually condition your burette and get it ready if we're going to carry out a titration in the lab, which we are not this year, unfortunately. But if you are in chemistry lab, that's what you would do. And you're going to add the solution until you reach the end point and you see a color change. The most common indicator I use is phenolphthalein, which once you get to the end point, if you're adding a standard solution of sodium hydroxide, it would turn pink. They're showing maybe like a bromothiamyl blue or something here where they're adding an acid to it until it turns yellow. Alright, so let's take a look at some titration curves. It's a graphical depiction of pH versus the volume of the titrant added. And let's see here. So this is a strong base being added to a strong acid. And your pH meter would be down in the analyte solution. So it starts off being very acidic, and as you add more and more known concentration base to it, eventually it becomes neutralized, and then beyond that it becomes more basic. Now the equivalence point is going to be the point where the slope of this line is at its greatest steepness, and right in the middle of it, and that happens at a pH of 7 for strong versus strong titration, strong acid, strong base. Now if the acid is strong but the base is weak, then that shifts, the shape of the graph pretty much stays the same, but it shifts the equivalence point down to where the equivalence point is acidic. And that should make sense to you, because if you mix a strong acid and a weak base together, remember you get a weak acid as the salt, and it's kind of a similar thing here. Alright, this one is a weak acid being titrated with a strong base, so you still start off acidic, but this time the equivalence point is shifted up to be basic. And then you can get into some weird stuff when you start titrating weak with weak. Sometimes the equivalence point will be about at 7, but sometimes it might not be. There's an overview of all of those different shapes of titration curves. Alright, and then we're going to do the titration calculations. So the most important thing to realize is that you are carrying out a stoichiometric calculation when you do titration problems. And they're easy if it's a 1-to-1 ratio. They're not easy if the ratio is something other than 1-to-1. So to identify if the ratio is 1 to 1, you got to write the balanced equation first. Then we're going to convert from molarity and volume to moles of the known solution. Then we're going to convert moles of the known to moles of the unknown, and then we're going to use the molarity equation again, using the known volume of the unknown solution and the number of moles that we calculated to find the molarity, or the concentration. So here's our first example problem. So we have this lab experiment. There's 20 milliliters of ammonia that's being titrated to the endpoint using 15.65 milliliters of 0.2 molar hydrochloric acid solution. What's the concentration of the aqueous ammonia solution? So in order to work this out, we're looking for the concentration of the ammonia. Remember, the brackets mean concentration of whatever thing in molarity. Here's our known quantity. So the first thing that we'll do is use the molarity equation to figure out the moles of the known. Then we're going to convert from moles of the known to moles of the unknown using stoichiometry. And then we'll use the molarity equation again to find the concentration of the unknown solution once we know the moles, and plugging in our liters from the information given to us. All right, leads into the saying, when in doubt, mole it out. If you can solve for moles, you usually can solve for everything else you need to solve for in chemistry. All right, so here's the molarity equation. Solve for the moles of hydrochloric acid there. And once you know the moles of hydrochloric acid, do some stoichiometry using the coefficients from the balanced chemical equation, which is conveniently 1 to 1. So, hey, look, it's the same number, but just moles of NH3. Can't drop that, especially if this calculation, especially if the numbers, the coefficients up here are not 1 to 1 to 1. Okay, and then the last step is to do moles divided by liters for the unknown, and that gives us 0.157 molar ammonia. All right, here's a second problem. So we got 20 milliliters of 0.3 molar sodium hydroxide neutralizing 30 milliliters of sulfuric acid solution. We want to know the molarity of the sulfuric acid solution. So we'll write the equation. Notice that the ratio between sodium hydroxide and sulfuric acid is 2 to 1. Our unknown is the concentration of the sulfuric acid. There's our knowns. So our plan here is going to be very similar to the last one. We're going to use the molarity equation with the known to solve for the moles of the known solution, convert moles of the known to moles of the unknown, and then use the molarity equation for the unknown solution to find the concentration of it. Because we'll know the moles from this calculation, we'll know the liters from the given information in the problem. All right, so first thing up here, we write the equation, write the reaction, and then we'll use the molarity equation to figure out the moles of the known that were used. So here's that amount, and then we will use stoichiometry to convert the moles of the known to the moles of the unknown. And once we know the moles of the unknown, we can calculate molarity with the molarity equation of the unknown, because now we know the moles. We can divide it by the liters of the unknown to find the molarity of the unknown. Here is the last sample problem. So how many liters of a 1.5 molar sulfuric acid solution are needed to neutralize completely 120 grams of sodium hydroxide? Now, this is different because they don't give you a concentration or an amount of sodium hydroxide in liters. They give you the amount in grams. So we still need to get to moles of sodium hydroxide. So this time, after we write the reaction, we will have to do a grams to moles conversion for the sodium hydroxide instead of using the molarity equation. So when I do that, I just use the molar mass to convert grams of sodium hydroxide to moles of sodium hydroxide, and then the remainder of the process is pretty much identical to the last problem. So let's do that. So first off, convert our grams to moles using the molar mass of sodium hydroxide. Then use that number of moles of sodium hydroxide to calculate the number of moles of sulfuric acid needed to perform the neutralization. And then use the molarity equation. This time we're solving for the volume of the sulfuric acid. And I recall to do that, maybe cross multiply and then divide by 1.50. And you should end up with 1 liter of sulfuric acid as your solution. All right, and the last thing we'll talk about here is the topic of buffers. So a buffer is a solution that resists changes in pH with the addition of acids or bases. So a buffer solution is going to contain a solution which is a mixture of a weak acid and one of the salts of that weak acid. So a common example of that would be a mixture of acetic acid, HC2H3O2, and the salt sodium acetate. So remember that the acetate is the Bronsted-Lowry base of the acetic acid. So when you dissolve those, you get both the acetic acid and the acetate ion in solution. And when you add an acid to that mixture, the acid's going to have H plus in it. It will react with the acetate and it will make acetic acid. Well, you already have acetic acid in the solution and it's a weak acid, so it doesn't extensively ionize. So a lot of that H plus that was added, maybe from some hydrochloric acid or something, gets converted to acetic acid, and only a small percentage of the hydrogen ions from the acetic acid actually ionize and go into the solution. So you have effectively decreased the effect of adding the H plus by probably 95%. When you add a base, the base is going to react with the acetic acid in the solution and it's going to make acetate. And the acetate is, remember, it's going to be a weak base because it formed from a weak acid. So that is weakly basic, but it doesn't add as much basicity to the solution as if the hydroxide had just been released to freely go around and dissolve in the solution. So buffers resist changes in pH. Thanks for watching.